Yeah. So good evening, everyone. So this is the tu- tutorial sessions for the NPTEL course on FEM modeling of welding processes. So this is our tutorial session one, and I am Jia Krishnasanathar. I will just show the slide here. A PhD scholar at the Indian Institute of Science, who is currently working on magnetic structures. So since the first week of the course happens to be mainly theoretical, we will be only discussing some of the basics. We'll just review the slides provided by the professor himself, Professor Swaroop Bagh. Let me just write it here. This course is offered by Professor Swaroop Bagh, IIT Guwahati. From the next week onwards, we'll be discussing quite a bit about the session here. So in the first week, the lecturer covered the properties and modeling approaches for welding processes, process modeling and optimization. And then it was a discussion about fusion welding and different approaches also such as soldering and brazing. And then it ends with the solid state welding processes. So what I'll do is I'll just open the notes offered by the kindly given handed out to us by the profession. And I'll just go through some of the important slides, which essentially forms the bedrock of this the welding as an introductory welding processes. So I will just turn off the video so as to preserve the bandwidth. Okay, so we are well aware that in order to produce a finished good, we require raw materials which are further processed through various different stages, intermediate stages, which ultimately results to the finished product. And in industrial processes, various mechanical or chemical procedures are adopted, and just to so this is mainly produce something on a large scale. We require raw materials which can be either extracted from the nature, or we can also produce in certain lab settings. And to produce metal, we require the raw mineral ores to be processed through various steps such as smelting and alloying, and then which are eventually fabricated into parts which can be assembled into a finished or the final product. So some of the metal classes of metals which are useful for our purposes are ferrous, which consists of iron as the main constituent, non-ferrous, which are iron, uh, which are other than iron. And steel is mainly iron, which contains carbon less than 2%, cast iron, which contains carbon more than 2%. Copper is very much used in the electrical industry to, to prepare, to draw wires and for circuiting purposes. Aluminum alloys are used in automotive frames in aerospace industry as well for designing for as a structure for say for the for the fuselage and all, mainly because of its low weight and high strength. Nickel alloys have this property that it has outstanding strength, and it's also very much resistant to corrosion. Titanium alloy, as you might be knowing, that it actually can sustain and withstand very high temperature, uh, and they are widely used in in say very precision equipment as well, also in the manufacture of engines and all. So some of the other alloys which are superalloys have high strength, grip resistance, oxidation, and corrosion resistance, static resistance even at high temperature, which are primarily used for jet engine, rocket, and nuclear application. Some of the important physical properties which are necessary for the material to have are thermal conductivity, which is the property of a material to conduct heat through it. And we also have high thermal conductive materials such as copper, aluminum, silver, gold. And those materials with low thermal conductance are polymers and alumina, which can be used for insulation purposes. Thermal expansion is the change in volume in response to change in temperature, and it creates thermal strain in solid. With regard to the mechanical properties, we have some of the quantities which are strain, which is essentially measure of a deformation of a body, and stress is how the body reacts to the applied um, load, which is responsible for deforming the material. And we have different measures for strain, for stress. And so given a plane, we have two components of stress. One will be which is normal to the plane, which is called normal stress, and the other is the one which is tangential to it is called the shear stress. And plasticity is, so as we are very well aware that material tends to, a solid tends to have this property of elasticity. In some materials, it will be very high, and in others, it won't be as much. So those materials we call it extremely brittle materials. Elasticity is simply the property of a material which tends to bring it back to its original shape once we remove the force which was applied to it. Plasticity is essentially that the body retains its deformed state despite the removal of the applied load. Toughness is the measure of or is the property of material to resist fracture due to high impact load, and resilience is the amount of energy when deformed elastically and it and the release upon unloading. So creep is another phenomenon which is when a mattress, even when subjected to a constant stress at elevated temperature for a long period of time, it will create time-dependent deformation, which is essentially permanent in nature, and it will go on till it eventually reaches ruptures, even if the applied stress happens to be below the yield strength at that temperature. Fatigue is when the material undergoes several cyclic stresses, and despite the load being within the yield point stress, it still uh, uh, it still it fractures. And hardness is the resistance to wear or scratching. There are various different ways of modeling any physical system. First of all, we start with a very mathematical perspective. We first have what is known as an equilibrium system, for which we require certain governing equations. So in order to construct those equilibrium equation, we could adopt two different approaches. The energy approach, where we construct a general energy function for the entire system, and then using the principles derived from the calculus of variations, we can obtain the governing equations. And the second approach is what we call as the forced balance approach, which very much follows from the classical Newton's law of motion. And we may see that we have certain quantities in the equation which is very specific to a system, and those are known as constitutive equations. So in a general solid body, we require a constitutive equation to relate this stresses with the strains. And in other, say, if you're performing a heat transfer analysis, then we require a constitutive equation to relate heat flux to the gradient of the temperature. And then once we have our given equation, we require certain boundary conditions to make the problem a well-posed problem. And if the problem happens to be time dependent, then we may also require a set of initial conditions. So an important an important requirement in physics-based modeling is the determination of the constitutive laws. So constitutive law is very much dependent on which system we are modeling, and it could also depend on various other factors such as temperature, what is the ambient temperature of the process being performed. So in order to obtain that constitutive relation, there are multiple approaches. One is what we call as the phenomenological modeling, in which we first carry out a series of experiments on a physical system and then relate quantities, which are, say, if it's solid mechanics problem, then then we'll try to derive a relation between stress and strain based on the experimental data. And then what we do is we also include certain variables which are based on physics called as internal state variables. And the other approach to the for constitutive modeling is what we call as physics-based approach. In that case, we use tools driven from actual physical laws so as to construct a constitutive equation from the bottom up, which means from very micro scale to at the level of mesoscale or macro scale. So for linear systems, or one of the simplest constitutive relation for solid mechanics studies is what we call as the linear elastic. In that case, we require two properties, at least two, two properties which define the metric, one of which is Young's modulus, the other is what we call as the Poisson's ratio. So in physics-based modeling approach, we start with micromechanics model, which takes into account more finer detail of the material structure at grain scale. And after that, we average the quantities and we pass it on to the continuum model through a well-known process in the theory of composite, which we call as the homogenization theory. So the mechanical model has this feature that it can provide local variation of so I see someone has joined. Could you please introduce? Is it Mabin? Could you please introduce yourself?
Hello.
Yeah. Hello. Yes.
Hello. I'm Mebin. I'm from Kerala. I'm currently
Okay.
working on analysis, so designing and analysis. But I have some. I need some clarification in fundamentals. So that's why I joined this
I see.
course because
Okay.
modeling of welding is very crucial thing because many of the parts are modeled as a
Right.
single piece, but
Right.
practically welding is there. So I want to
Yeah.
study more about how the things are working.
I see. I see. So, are you a master's or PhD student? May I just know?
Hello.
So, could you please let me know, are you a master's or a graduate, postgraduate?
Uh, I'm, I take my master's in thermal engineering.
It seems you are not very audible, so could you please
Hello,
also,
sir.
yeah, yeah. It seems you are not very
Uh,
audible.
okay. My internet connections are
I
poor
see. Yes.
and
So one way is, could
uh,
you just type it out in the chat box here?
okay, okay, sir.
I think that would be, we also have Manoj Kumar here. Hello, Manoj. Please introduce yourself. I hope I am audible.
Yes, sir. You are, sir.
Yeah,
Let
yeah.
me share.
Okay.
I can't find where the chat box is because
I see. Huh. So it's better if you please type so that, yeah, just a brief, very, a very brief introduction. So yeah, it will help me to know you. Yeah. I have been just reviewing the theory which was discussed by the professor in the first week. So since there is not much, I mean, it's all theory, so I have just pulled out the slides and going through some of the important details here, which are necessary for our further study in this course. So maybe from the next week onwards, I think we will have more say theory. I mean, we'll start the basics of finite element approaches. So I think I'll be mainly writing. So we'll be taking notes as well. And
मतलब फर्जी तो हटा देना इसको हटाना चाह रहा हूँ मैं एक गियर ट्रांसमिशन वाली को बाकी कौन सी है हाइड्रोलिक मशीन ओके मैकेनिक्स पूरी ठीक है आई सिंगल ठीक है ये स्मार्ट मैन्युफैक्चरिंग मटेरियल क्या है सर ये रेफरेंस बुक कॉन्फ्रेंस वाली नहीं ये रेफरेंस बुक कॉन्फ्रेंस वाली है तो इसमें लिखना पड़ेगा एलएनएमई लेक्चर नोट्स इन मैकेनिकल इंजीनियरिंग का ये दोनों ठीक है ध्यान में मेरे को क्या लिखना है इसमें एलएनएमई तो मेरे को कंफ्यूजन नहीं है ऐसी वाली हटानी है और एलएनएमई का बाकी ओके वेल्डिंग का ठीक है और ये भी ओके हो गया
hello, Vishal. Is it Vishal?
एक वो मालदीव की कॉन्फ्रेंस में क्या क्या किया था पेपर पढ़ा था और एक लेक्चर
Okay, so yeah, essentially I've been going through some of the ideas that will just about this processing technologies and how the physical and mechanical properties. And I just briefly was discussing about the different ways of constitutive modeling. One which is what we call as the physics-based modeling, and the other is what we call as the phenomenological modeling. Phenomenological modeling takes into account the variation of it takes into account the real life data which we obtain based on certain experiments conducted in the lab. And it usually does not tend to be physically consistent or physically rigorous, but yeah, it does. Uh, relate certain properties in the equilibrium equations quite well. So based on the different, say, different levels of modeling, we'll be able to refine our constitutive model. So the finer experiments or uh, the finer we go, the better our model tends to become. So it's like we may have heard of what we call as the Ogden model. So it's a model which is very much used in constitutive modeling of rubber. So it is a very general model. However, and it was developed just based on the physics approach. And but however, it did tend to use some of the experimental data. Yeah. So at the multi-scale, what we have is you see that there are different four levels as is mentioned here. We start with continuum, so then it goes to microstructure, to atomistic, and electronic structure. So electronic structure, these simulations are essentially used to determine the wave functions of how where all uh, the electron can be found in the particular outer shell. So and then further, just a level high is what we call the atomistic model. So there are multiple ways of doing such simulations. One is what we call as the MC is the Monte Carlo simulations, and MD is just the molecular dynamic simulations that can be done. And further ahead, if we move, it's like microstructure. So microstructure is something a level just below continuum. So in microstructure, we also tend to study how the material will look like, how the particles are arranged in a particular region of study that we consider. And it can have say we can use either heterogeneous approach where a microstructure at different points in the body will tend to have different distributions of the particles. And one is what we call as the homogeneous approach, so that at one particular point where the microstructure it will be, it keeps on repeating throughout the domain. So once we average out the properties at this level, then is what we define as the continuum theory of the continuum theory. So such that at that particular location, we will just tend to have an averaged value of, of of the immediate neighborhood of that point. And in this, we have different approaches. Either if our body or if our object of study, if the system happens to be solid, then we use either say finite element based simulations, or nowadays there is also the usage of finite volume approaches to study this. However, if we have say fluids, then we'll use the continuum on computational fluid dynamics uh, to study it. There are various techniques here as well. Either if the system happens to be say very say 1D, then we could use finite difference, or and for a simple setting. And if the geometry happens to be complex, then we will have to do finite volume approach or even finite element approaches to solve fluid mechanics problems. So there are certain limitations of such simulations as well, that continuum models are good in general, but they may not be adequate, say if the properties or if the material distribution does not tend to be uniform in the body. And it also assumes that there is no voids in the body. So say if we are modeling composites which has enough voids, uh, then performing continuum mechanics, continuum model, or taking or utilizing continuum models to study won't be a good idea, because voids tend to play a significant role in essentially in say reducing the strength of that body. So so in that case, we may require atomistic information in those regions of high deformation or discontinuity. So other say for quantum models, we usually tend to use finite element approach for doing solid mechanics simulation. However, say if we also wish to include voids or void like or voids in the system, then one of the approaches that have been gaining quite interest is what we call as peridynamics. So peridynamics method is able to even model uh, the discontinuous system. So and since it does not actually take into account the derivatives, say the derivatives of the displacement at every point, because if the body happens to be discontinuous, then the derivatives is not cannot be defined, isn't it? So yeah, that is a subject of another study. So I just wanted to introduce here. So for if the domains happens to be fairly small, which is a 10 to the power 6, 10 to the power 8 atoms, and if you are simulating the system for very small time period, then molecular dynamics approach can be used. However, in all real world problems, it's we cannot actually perform molecular dynamics simulations because of the enormous enormity of the number of particles which are present in a system. And based on approaches, we can have hierarchical approach where where we use information at one scale to generate model for larger scale. And this typically is done in multi-scale modeling as well. So we use the information at the micro scale to construct something at the meso scale, and information at the meso scale to move to the macro scale. Or otherwise, there is something known as a concurrent approach where we perform simulations at different length scales simultaneously. And the relationships, as we mentioned here, that the length scale are dynamic. So there are so multi-scale. Say if we use continuum methods, then the material is assumed to be continuous. This is the most fundamental assumption, and we treat the properties as field quantities. So physical field quantities are something which is defined at every material point in the body. Then we construct balance equations, which we for which we use certain phenomenological equations to predict the properties of the system. It does have its advantages that it can handle systems of any size and dynamic process on longer timescales. However, say if we are we require parameters for the constitutive equation are have to be determined beforehand from experiments or from some other low scale methods, which are not easily obtainable. And it does not explain things which take place at or phenomena which take place at a macro level of details. So and also it on the so if a process happens to be very dynamic in nature, then this continuum method would not be able to give us the detailed details of how the properties are evolving. So in multi-scale model, we have said the connection between different models. There is one upscaling approach, in which case we use results from a lower scale calculation to obtain parameters from higher scale method. So this is like deductive approach. So say we use the phenomenological constants from atomistic simulations for to be used later in continuum model. And in the down scaling, we move the other way. That we first have the higher scale information, and then use it to go further down the line at the from the perspective of length scales. So in this case, what happens? There is non-uniqueness in the problem. That is obviously true. The reason is because for the same, for various different microstructural level of information, we can still have the same higher scale information based on averaging, because since it involves when we move from a lower scale calculation to a higher scale calculation, we are essentially averaging out certain properties. So it will, there, I mean, in a sense that we can have, say, on an average, we get some quantity, but if we move on the other way, we can we can have different distribution giving us the same average. So that is one of the cons of the multi-scale model, which tends to use downscaling approach. And for there are certain challenges at the atomic scale, that we have very large number of degrees of freedom, and at the interface there is mismatch of dynamic properties and other issues. Then we have multiple time scales, and there is also an interdisciplinary nature of continuum dynamics, quantum mechanics, and then we have classical particle dynamics, and various lattice approaches, and quantum mechanics and thermodynamics. We can also have atomic scale plasticity, which is because of the dislocations of the lattice points, which could be atoms. So because of that, yeah, there could be dislocation. So it leads to plasticity in the material. And we also have algorithmic issues in large scale couple simulation. This is mainly because of the enormous amount of complexity in the for a couple system. So say some approaches could be n to the power cube. So just say if you have 1,000 particles, the complexity order could be 10 per 9. And so you see how exponentially the complexity grows. So statistical and data in the statistical and data-driven approach will be we require data, obviously, and for this we require various sensors for various different purposes. Okay, and now let's just discuss what is the process modeling optimization. So there are certain research techniques here, that wavelet packet analysis, Hilbert-Hung transform with wavelet analysis, fractal theory. Fractal theory is the theory where any any configurations tends to repeat uh, no matter how much we zoom in. And there is also the current the contemporary world, there is also growth in the uses of artificial neural network approaches, and even support vector machines, all of which are a part of what we call machine learning techniques. Okay, so now let's just start the topic of welding processes. So welding and joining. So we require welding mainly to uh, say assemble particles. I mean assemble components to give us a complete finished product, if we call that. So in joining, approaches could be various types: welding, brazing, soldering, or bonding, etc. And for mechanical joining, we can use fasteners, rivets, etc. And this could take place at multiple scales: macro scale, micro scale, or nano scale. There are also different types of liquid welding: liquid state welding, solid state welding, and solid/liquid state welding. It depends on what the nature of filler material, or during welding process, what will be the state of the filler material. So here is a hierarchy of the types of welding, that we have three major classes, as we explained here: fusion welding, pressure welding, and friction welding. Fusion welding actually involves fusing one material into another. This could be of two different types: homogeneous or heterogeneous. Homogeneous tends to have either gas welding, electroslag, high energy beam, and electric arc. and heterogeneous could be can be brazing, soldering, and friction welding is when we tend to create enough temperature for the material to for a filler material to liquefy just using friction. When in pressure welding, we actually subject the metal to a very large scale, very huge pressure to for welding purposes. Now, is it possible to bring metallic surfaces together? So only grain boundaries separates say two different metallic surfaces. So we can still join them if we apply a large force. So this is the ideal case to conduct welding. That the ideal case is to have practically metal surfaces which are contaminated with layer of oxides. Deals with the phenomena associated with welding processes, the formation of weld bonds, which are fusion welds and solid state welds, and which will be differentiated based on how the metallic bonding mechanism physics is. For the principles of fusion welding, they are created by the collision of molten base materials mixed with molten filler metals. And the metals must be heated melting point for fusion welds to be produced. Phase transitions are inherent to the to these processes. In those regions, we'll have what is known as the heat affected zone. The cooling of fusion zone is associated with distortion, residual stress, and metallurgical changes. And the principle of solid state welds are that it takes place at temperatures below the welding point and can be created by macroscopic or microscopic collisions of the materials in the solid state. So based on electrode property, we can have different types. So we'll not be discussing right now here. I would just be moving on to the enthalpy of melting. So the heat required to melt a given volume of weld is equal to the heat required to melt the solid plus latent heat of fusion. So first of all, we actually need to increase the the solid from its ambient temperature to the melting temperature. So for this, we require rho into Cp into delta of T, which is Tm minus T naught. And then at the melting temperature, we further require more energy for phase transformation. So for the solid to change its phase from a solid to uh, liquid or molten form. Then say if we have this base material is where we'll be attaching some other material, some other yeah, some other component. Then we have this HAZ, which is the heat affected zone, and this is the fusion zone. So this fusion zone will be much higher in temperature, and heat affected zone is will have less temperature in that. However, it happens to be at the yeah in between fusion zone and the base material. Now, the energy to produce bonds can be in the form of heat to melt the metals, and the version of energy sources are electrical sources, which uses electrical energy available from DC or AC source. And we can have arc welding, resistance welding, and electroslag welding. Chemical source in this case, we can utilize the what you call chemical energy stored in the bonds. Say if you are using oxy-fuel gas welding, then we require oxygen and fuel, and which as a by virtue of the combustion, it creates enough energy to support this welding process. And other sources could be optical sources, which is say using high powered laser beams. We can induce say melting of the filler material and also the base material, so that yeah they will tend to form a weld, so to speak. In mechanical sources, we can utilize the mechanical movement. Say if one surface is rubbing on the other surface at very high pressure. So this would also result in he- heat due to friction. And we could also use explosions to create enough energy for the weld to form. And these solid state sources are characterized by the lack of motion in contrast of mechanical processes. And in work, then we first start with arc welding, and arc welding happens to be the electric source. So the powers, and here we require some certain amount of power source to deliver either controllable current at voltage according to the welding process being used. We can have either constant current or constant voltage. We come to what's the role of shielding gas. So shielding gas, it helps to protect the arc and molten weld pool from contamination by the atmosphere. Otherwise, say due to contamination, it will reduce the quality of the weld, and which could further lead to say corrosion and all later, and the welding won't be as strong, and it's very much likely to fail. So now the common shielding gases that we use are argon, helium, carbon dioxide, and oxygen. And so they are 100% required for certain applications and could be mixed uh, together in different compositions. We have to specifically look at the reactivity as ionizing potential and thermal conductivity. And the other gas welding technique was what we call the oxy-fuel. So one example here is oxyacetylene gas welding. So here we use acetylene gas, which is C2H2, and oxygen in the welding nozzle here. And the proportion of gas will decide the nature of the flame. And if it's say 1 to 1, if the ratio happens to 1, then we have what we call as the neutral flame. And if in certain case, if we have a higher acetylene, then it will become slightly carbon rich. So we call it carburizing. Okay, and then we also have oxidizing flame, in which we'll have more oxygen than required for a neutral flame. Then we have this shielded arc welding. Here we use consumable electrode, and then we have all this welding process being carried out. And then gas metal arc welding. There are certain more different types of welding. I think it's let's go through it, and then get we'll discuss some of them. And let's start with welding and brazing or soldering approaches. Okay, now let's discuss the about welding, brazing, or soldering. So the difference between welding or brazing or soldering is that in welding we'll have the metal components will be joined through fusion, which means that both the filler material and the base material have at the point of welding has to be molten. And this will or through the recrystallization of the base material by applying heat, pressure, or both. In brazing or soldering, it's only the filler material which melts during the processing. And the difference uh, between brazing and soldering is that in soldering we'll have the metals are bonded together using a non-ferrous filler material, for which the melting temperature happens to be less than 450 degrees Celsius. And in brazing, the filler material is higher than 450 degrees Celsius. It's considered to be a brazing process uh, rather than a soldering process. In brazing, what we have is that it is distributed in liquid form between two or more closely fitting parts by capillary reaction. Okay? So, and what happens is that the filler material is brought slightly above its melting temperature, which then interacts with the thin layer of the base metal, which is known as wetting, and is then cooled quickly to form the seal, seal joint. It's because of the capillary reaction, which actually pulls both the melting brazing alloy into the space between the parts being joined. From the advantage of, advantage, disadvantage of brazing are that it can join virtually any dissimilar materials or metals, and we can have the bond line which can be very neat in appearance, and brazing does not melt the base material, and we won't have any distortion in the weld, and we could also use this approach to join non-metals such as ceramics, which can be easily brazed to each other or to metals. So there are certain limitations as well, that the brazed part may not be put in an environment which can exceed the melting point of the filler material, and it requires higher degree of base metal cleanliness. Otherwise, it will just reduce the quality of the weld being formed. And it also lacks from this thing what we call as the aesthetic disadvantage, in that the joint color will often be different from that of the base metal. So from an aesthetic point of view, it does not look good. Now we come to the last part of our review session here, which is the solid state welding processes. So the physical aspects of solid state welding is frictional heat generation. As I mentioned, it is mainly because of the say friction heat generated due to friction between, as one surface is say rubs against the other surface, and that too at a very high pressure or some other mechanism, because we need to create a high force to actually affect the process. And we also have this plasticization of material, which is because of the stirring action, and the temperature is limited to below the melting point, and there would be heat conduction as well as and also the solid state phase deformation. It could also lead to distortion and the formation of residual stress in the welded material. Now, first, to understand what is the macrostructural point of view and the surface condition of the workpiece, isn't it? So, at the at the macro scale, microscopic scale, what we have is we have this. Say we have given a base metal. Just above that, we'll have what is known as mechanically or chemically affected metal, and we would have say multiple layers of say the first layer happens to be the oxidized layer, and a layer above is the contaminant layer, and this generally tends to be the surface conditions of any workpiece. Okay? And also asperities of the surfaces has to be collapsed. So say we can, and both these layers have to be removed. So for to breaking this contaminant layer, it can be done by mechanical action. And we can break down the metal oxides by dissolution into the matrix into some other say some other solution which will just clean this oxidized layer. Then we have this local yield stress which can be exceeded on this contact surface, and surface deformation would also be used to create contact. And the bonding mechanism of the solid state welding is will have the formation of localized melting, diffusion process, recrystallization process, adhesion, interfacial reaction, and interfacial morphology. So for localized melting, we could use explosive welding, which will tend to create enough energy in the neighborhood of the reason to be welded. When we could use friction, as I had mentioned, and we could also have this ultrasonic welding. This is a passing very high frequency acoustic waves through the material, which will just simply shake those say the atoms on near the surface. When friction heating due to welding, it can cause localized melting, and it could also reduce intermetallic compounds, which may lower the bonding strength. Diffusion is generally a thermally activated process, which is related to the material properties and applied temperature time. And recrystallization is when the intimate contact between two mating surfaces can be achieved. Say through this recrystallization process because of say the migration of grain boundaries. So it's when one boundary happens to due to certain process we are able to alter the entire the grain the grain landscape, that the reason where we would like to have the welding. And in solids, and then there is this adhesion. So adhesion, it could result from the atomic attraction which has been it's because of atomic attraction which will have this bonding mechanism for any kind of solid state bonding techniques. So as we recall from the energy, you may you may have heard of that atomic energy potential between say two between the nucleus and the electron, or likewise say between two atoms. That it will tend to have some graph which will fall rapidly, and then it will increase rapidly as the distance increases. So which means that at a very if we say if we have two atoms and we bring closer and closer, then it tends to attract till a certain distance, post which it simply tries to repel. And then we'll have to bring these two clean surfaces to be within a distance of 10 angstrom. And then we have this interfacial reaction where there is a reaction of oxide films with weld metals. The solubility of oxide at interface is important. And we could have reaction between two weld metals, and this will lead to the formation of intermetallic bonds, which could be harmful to joint strength. And there could also be phase transformation during the welding process. And the interfacial morphology is what how the morphology looks like from the surface. So it is a unique characteristic in explosive welding in the form of planar, wavy, or molten layer interface. And it will also depend on how fast the flyer plate moves with relative the collision point and at which angle it is subjected to. Collisions is produced at the flying surfaces by the application of high frequency vibratory energy, and this will take place while the work pieces are held together under moderately low static pressure. It can produce a weld by oscillating shear forces at interface between the two metals which are joined, and this it takes place as they are held together under high pressure. And due to localized temperature, could also result from interfacial slip, isn't it? And due to the movement of grain boundaries, which leads to a change to the creation of this plastic deformation. And the temperature can also be influenced by, say, power, how much energy we are supplying to it, based on how tightly we are holding it, and and also the thermal properties of the mesh. And we could have localized plastic deformation. Certain other feature can also take place at the interface, which are recrystallization and phase transformation, etc. So some of the process parameters in ultrasonic welding are ultrasonic power, how much power we are expending to weld the system, and then clamping force, for how long we are welding, and what is the nature of what is the frequency of the oscillation that we are being provided to the system. There are different types of friction and there are other welding process techniques as well, such as friction stir welding. It's a green technology due to its energy efficiency and environment friendliness. And then we come to the diffusion bonding, in which case you have a solid state diffusion welding process that process the collisions of the playing surfaces by the application of pressure at elevated temperature. So in this case, everything takes place through diffusion. Diffusion is just, as we call it, process by which, say, molecules from the region of higher concentration will move to molecules to the region where it has a lower concentration. So that's why it says that it does not involve any macroscopic deformation or any relative motion of the workpieces. And a solid filler material may or may not be inserted between the playing surfaces. So one of the aspects of diffusion welding is preparation of the surface for which the welding has to be performed. And we also have this explosive welding, in which case we use the explosive force to create metallurgical bonds between two components. And since the time of impact will be very short, so this would lead to very high adiabatic heat rise. So that's what we see here, that we have chemical explosive, and then we have this flyer. It will just heat at a very high speed, and we have the substrate, which is also like what we had that base mentioned. And this will be the deformed zone. An application is the cladding of steel plate with a thin layer of corrosion resistant material. So explosive welding and jetting process. So in this case, we'll have explosion on the flyer plate at high pressure pulse is generated. This pulse propels the flyer plate at a very high velocity. And the jet is the product of the collision of two metal surfaces. It allows two pure metallic surfaces to join under extremely high temperature. And in the occurrence of welding will also depend on what piece of metal plate is colliding at which angle with the parent metal plate. So there is one metal plate and this will be the other metal plate. So we are creating this explosion uh, able to make it amenable for melt, and then it will just stick, will just attach to this substrate. That's what goes on here. And then we also have this electromagnetic pulse welding. In this case, we use electric, I mean, this Ampere's law, which is essentially, say, when we have a current flowing through a conductor, then it produces the magnetic field in the vicinity, or not in the vicinity, just about itself. So if we have, say, two conductors which through which current is passing, they will exert force on one another. And say if you have two infinitely long parallel conductors, then this is the relation of the force which relates it to the separation distance between those conductors and also the currents passing through the individual conductors. And we will and due to electric flow, current flow, and also the magnetic flux, it will also result in a second type of force, which are known as Lorentz forces. So in this case, the energy has to be stored in capacitor bank, which is essentially two plates with charges distributed, I mean, on other sides with opposite charges on the others. And this is through this will be charged through a DC power supply. And the energy is discharged through the work coil by triggering the spark gap. The damped sinusoidal current will produce a transient magnetic field. And welding is completed in a very short amount of time, say around 50 microseconds. So the work shears in the vicinity of the work coil will cut the transient magnetic field. And what we say is that the induced that it will also lead to the it also lead to induced electromagnetic force, because of which there will be certain loops, current loops, what we call as the eddy current, which tends to the oppose the external magnetic field because of what we call as the Pen's law. Okay, so the induced electric current, eddy currents depends on the material properties such as conductivity and permeability. And finally, once this process is done, then we'll have the work shapes will be repelled away from the coil or towards each other, thus creating an impact due to the Lorentz force. Okay, so yeah, so I think with this we'll be ending today's session. So today's session was essentially a very general description of this process. I just went through the lecture notes of the provided by the instructor, and from the next time onwards, we'll be discussing the mathematical basis of every topic. Yeah, so I think I'll stop recording and then let's meet in the next on the next Tuesday. Thanks.